So, limit of a function, what is a limit? So we got three functions given by f of x, g of x, and h of x. And we got a table of values for each of them. And we're showing you the values as x gets close to 2 in this table. So you can see we're coming at 2 from below, 1.8, 1.9, 1.99, 1.999, 1.999, etc. And then we're coming at 2 from above, if you look at it as 2.2, 2.1, etc. And we're looking at these values. All right, so microphone is on. If you examine the column of the values of x, you note that for the upper set of the values, as you go from top to bottom, the values are increasing. So we're looking at the x's. These values are increasing and getting closer to what? 2. For the lower set of values, as you go from the bottom to the top, the values are blank and getting. So as you go bottom to top, the values are decreasing and getting closer to the number 2. We say that the x values are approaching 2, and we express this as x, and then the arrow there means x approaches 2. Now, let's take a look at the columns f of x, g of x, and h of x and complete the following statements. As x approaches 2, what's f of x getting close to? Or what's it approaching? 3. For g of x, as x approaches 2, g of x approaches 1. And as x approaches 2, h of x approaches infinity, right? It's getting pretty big, so. Infinity. Not the greatest infinity symbol ever. We say the limit of f of x as x approaches 2 is equal to 3. We can also say that the limit of, now what is f of x? It's x squared minus 2x plus 3 as x approaches 2 is equal to 3. Mathematically, we don't want to write this out all the time. We write it as the limit as x approaches 2 of f of x equals 3. Or the limit of x as x approaches 2 of x squared minus 2x plus 3 equals 3. So can we complete this for g of x? So in words, what do we say for g of x? The limit of, I'm just going to use the same words, but so the limit of g of x as x approaches, I can spell it, approaches 2 is equal to 1, right? I mean, that's the value we saw on the table. Or the limit as x approaches 2 of g of x equals 1. Or we can state it, instead of g of x, we can use what g of x actually is, right? Which is x squared minus 3x plus 2. So the limit as x approaches 2 of x squared minus 3x plus 2 over x minus 2 is equal to 1. In general, we write the limit as x approaches a of f of x is equal to L, and say the limit of f of x as x approaches a is equal to L. If we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to a but not equal to a, right? So we can make the values of x as close as we want to a, and as we do that, we're going to get as close as we can to L, but we're not really going to get there necessarily. Okay, and if you go on, I'm assuming if you're here now, you're probably planning to do calculus post-secondary, then you'll do a more formal definition of limit, which we don't cover in 31. It's called the epsilon delta, if you want to go look it up. But there's the epsilon delta definition of a limit. Basically, it's just this. Okay, let's determine each of the following. So what's f of 2, right? Well, so all we do is we substitute in a 2 for x, and we work it out. So f of 2 is equal to, wherever I see x, I write a 2, which is equal to 4 minus 4 plus 3, which is 3. And we're going to do the same thing for g of 2. And for h of 2, right? So I mean, we can all work on it. You can do yours, I'll do mine. Okay, I got 0 over 0 there for h. I got 3 over 0. So 3 different situations arose, right? Maybe while you're copying that down, f of 2 exists. Right? F of 2 is equal to 3. The limit as x approaches 2 of f of x exists. We found that. And the limit as x approaches 2 of f of x is just equal to f at 2, right? It's the same as if you just evaluated f at the value 2, you get that value of 3. G of 2 does not exist, but its limit does exist, right? So we can get close to 2. We can't become 2 because then what happens? Your denominator becomes 0, and yeah, I know, I will apply. You can't do that! And h of 2 does not exist, and neither does its limit, though, right? So we saw that. Well, numbers are getting big. Now, we do have a little discussion to have on that about the limit doesn't exist versus, well, wait a second, we saw that it was the numbers were getting up really high there. And we'll have that discussion in a moment. Let's examine the graphs of these functions to gain a better understanding of the 3 different situations. Use your graphing calculator. You could use your graphing calculator, right? But I'm going to go to, I plugged them into decimal. So we can look at them here, right? We get a nice window and everything's good. And so there's the graph. You can sketch it out. Okay, that's the graph of x squared minus 2x plus 3. So it's not exactly on the window they said. Yeah, close enough, right? You can see what this looks like. So I'll give you a moment. You can sketch that out. I'll sketch it out. What do we got? We got like a vertex at 1, 2. Yeah, vertex at 1, 2. We got that 0, 3. Okay, so vertex here. That's at 3. Make a sketch of each graph below. All right, now what do we want to do? Let's just look at f of x bar. The graph of f of x equals x squared minus 2x plus 3 is a continuous curve. All the points are connected. When we draw that, we don't have to lift up our pen, right? We're not doing anything special. We're just drawing it, so it's continuous. Okay, let's take a look at g of x. Turn that off. Turn that on. So there's g of x. Now, what do we know about g of x, though? Right, like there should be something going on here, right? G of x, we got a problem. It doesn't exist at 2. All right, so what's going on here? Let's take a look. Let's trace out a point. So here, oh, what happened there? Ah, so 2, undefined, right? And notice the open circle. So when we draw our graph, we're going to have to put an open circle at 2, right? Because it's undefined. We can also notice the values as we approach 2, right? So here we are approaching 2 from below. You know, what are we approaching? You know, we're getting 0.9, we're getting close up to 1. If we approach 2 from above, so as we come down, and we get close to 2, we can see that our values are getting close to 1, right? That's the limit. Okay, so we're basically just going to draw a straight line. Where does it go through? It goes through 1, 0, and negative 1, 0. So only, whoops, I'm going to leave a little hole here. Okay, so there's our graph, and when x is equal to 2, this graph is undefined, right? So the graph of g of x is a line with the point 21 missing. The graph is almost but not quite continuous. In fact, we say that y equals g of x has a point discontinuity. Right? You see those last year? I'm pretty sure you saw those last year, right? So we have a point discontinuity at x equals 2 because we know that if x were 2, you'd be dividing by 0. Okay, and h, 3 over x minus 2 squared. So where's that? Let's bring this back in, hide that, reveal. And there's the graph of y equals 3, whatever, h of x. There's the graph of y equals h of x. And we can see, which we knew from the table of values, that as you're getting close to 2, your y values are getting really high, right? Very large. So.
Yeah, that's
Okay, and there's that graph. So the okay, the graph of h of x is not continuous at x equals 2. In fact, it has an, what do we call that? An asymptote at x equals 2. Okay, so that's looking at things graphically. So, Bobby, when you're doing some of these questions, you might want to pull out graphing calculators and look at, so what does this thing look like, right? Or if you have access to a computer tablet, I think Desmos has an app you can get, maybe, and if not, it'll work on a tablet, so it's kind of handy, or a laptop. Determining the limits given the graph of a function. So here's the graph of a function. Use this graph to state the following limits. So the limit as x approaches negative 3 of f of x. So what happens as we approach negative 3? What are we going to say about this limit?
when it says approaches, I'm just when it says approaches, it can be like it's like both sides approaches, right?
Yeah.
It can be either side.
Well, we got to make that distinction. So we're going to start with does not exist. And that's what your book is going to say for a lot of these, right? Does not exist. And so now that brings up the, okay, but really, where is it going to? It's going to infinity, right? So I'm going to pull a page. So this is the 5th edition of Stewart's book. Stewart's the guy who wrote the book, right? This is the 5th. They're on the 7th edition, or maybe it's the 7th. I don't know, whatever. This is the next year's book, One Year Use University, where it talks about infinite limits, right? Because that's really what we're dealing with here. So it says, find the limit as x approaches 0 of 1 over x squared if it exists. Solution. As x becomes close to 0, x squared also becomes close to 0, where I get small numbers, and 1 over x squared becomes very large, right? There's a table of values. So you got 0.5, you put that, you get a 4, you get 25, 100, you put in, you got a million there. This is the graph. It's very similar to the graph we were just looking at, right? It appears from the graph of the function, f of x, shown in figure 11, that the values of f of x can be made arbitrarily large by taking x close to 0. You can get it as big as you want by making x smaller and smaller, right? Thus, the values of f of x do not approach a number, so the limit does not exist. Okay, so for the limit to exist, you have to approach a number. To indicate the kind of behavior exhibited in example 8, we use this notation. The limit as x approaches 0 of 1 over x squared equals infinity. Okay? This does not mean we are regarding infinity as a number. nor does it mean that the limit exists, right? So two things, the limit does not exist. The answers in your book for this section, when you get that type of situation, will say does not exist. Your answer will be does not exist, or it could be infinity. We'll take either. I'll take either on a test, unless you get it wrong by saying infinity when it really does not exist, and we'll look at that in a second. Simply expresses the particular way in which the limit does not exist. So it doesn't exist, but it doesn't exist in a particular way, which is that we can make 1 over x squared as large as we want by taking x close enough to 0. In general, we write symbolically the limit as x approaches a of f of x equals infinity. Okay. So for us, it would be the limit as x approaches 2 of the thing we had, and we would say infinity. To indicate that the values of f of x tend to become larger and larger or increase without bound as x becomes closer and closer to a. Let's see if I can just move this a titch. Move this a titch. No, I can't. All right, never mind. So, does not exist or infinity, right? So by that reason, right? So your book doesn't give that reasoning. I guess they save that for a year from now, for some reason, right? We will say this. And the reason we'll say this also is because when we come to curve sketching and that, it's important to know, well, where's it going? Because we're going to have to draw this thing. We don't have the calculator to draw it with, so we want to know what is its behavior. Okay, so that infinity. What's the limit as x approaches 0 for f of x? So, or 0. Pick a number, any number. That's halfway between 2 and 3, perhaps. 2.5, right? So all you say, hey, look, well, this thing's continuous, so the limit as x approaches 0. There's 1, there's -1, so there we are. It's 2.5. Okay, here it is on here. And what is the limit as x approaches 3 of f of x?
5.
Okay, so here's the question. What is f of 3? So if I say to you, here's the table, what's f of 3?
1.
1. What's the limit as we approach 3 of f of x? 5. Okay. So the limit is 5, right? Even though f of 3 exists and it's 1, the limit is 5. Because whether we're coming from above or from below, just remember, we can't do 3, right? When we say limit, we're saying as you approach 3, not when you hit 3. So as you approach 3, these values approach 5, right? Whether you're coming from the left or from the right or from below or from above, which are just different ways of saying the same thing. So now we're talking about left and right-sided limits, so coming from the left or the right. It's possible for a graph to have 2 different limits as x approaches a particular value. For example, in the graph shown below, the limit of f of x as x approaches 2 from the left is different from the limit as it approaches 2 from the right. The limit of f of x as x approaches 2 from the left is -3. Right? So as you're just going along this line, getting as close to 2 as you want, you're always going to have a value of -3. But if you're approaching from the right, then your limit is 1. Using limit notation, we say the limit as x approaches 2, and that minus sign says 2 from the negative direction or from below. Okay? So as we approach 2 from below, the limit is -3, and 2 plus means as we approach 2 from above. Or the negative means from the left, and positive means from the right. Okay, so negative from a negative direction coming from the left, and positive coming from the right. Since the limit of f of x as x approaches 2 from the left is not equal to the limit of f of x as x approaches 2 from the right, we say the limit of f of x as x approaches 2 does not exist. So this is a really, for real, it does not exist, not a, it doesn't exist, but it's infinity. This is it just doesn't exist because it's not the same on both sides. Which one do you pick? We have two different limits, so we can't do that. So using limit notation, the limit as x approaches 2 from below of f of x is not equal to the limit as x approaches 2 from above of f of x, then the limit does not exist. Okay, and that's a for real does not. That's the correct answer. Does not exist.
Question on the last page, what is the dot for on the graph?
On the last page?
Yeah, there's-
I don't know. I'm sure we'll get there.
I mean, like,
Oh, the previous page?
yeah, the previous.
Oh, the previous page. Okay, wait a sec. What dot?
At the bottom, like, on the graph, there's that dot, that green one. Keep going down.
I can't. Okay.
Yeah.
Oh, this.
The
Okay,
dot
so
dot.
this says does not include.
Yeah.
So this says that if that's f of x, that f of 3 is this value here, which is 1. And it's not 5. Okay, so the solid dot says this is the value for when x is 3, this is the y value, you open
But
the
it
dot.
doesn't really have to do with anything but the limits.
Yeah, it's for the limits. But it's just saying for some reason this function at 3 is defined as 1.
Okay.
Okay. But the limit as we approach 3 is 5.
Okay.
Okay?
Thanks.
Yeah, no worries. Okay, get that. Yeah, my pages aren't the same, we're split different, but. Exercises. The equations of 4 functions and their corresponding graphs are shown below. State the points of discontinuity of the functions, the equations of the horizontal and vertical asymptotes of the functions, and the limits of the function as x approaches the indicated values. Okay, so here's the first function, 2x plus root, did I do this one? No, actually I did this one here. So here's, now, so decimal does something a little bit weird here, right? So we have to, but if I trace points, so we say, at 0 it's undefined, right? I don't know why that, so there are limitations to our technology, right? But that's kind of what that looks like. So what is our point of discontinuity? 0. Okay, so it'd be, 0 and 2.5, right? So 0, comma, 2.5 or 5 halves. Equations of asymptotes. Are there any lines that the curve looks like it's going to approach but not touch? 2. So y equals 2. So as this heads off to the right, we got y equals 2. Okay, now what are we looking at? So we're looking at the limit as x approaches 0 from above, the plus. So what is the limit as x approaches 0 from above? So there's 0. So from above means from a positive direction or going right to left. So that limit is 2.5 or 5 halves. What's the limit as x approaches 0 from below or from left to right? 2.5 again, or 5 halves. So what's the limit as x approaches 0? 2.5, right? So if the left-sided limit and the right-sided limit are the same, then we have a limit. So this is 5 halves. Let's go here. What's the limit as x approaches -1 from above, right? Going from right to left. So -1 from above. What's the limit? So as you approach -1 going this way. 3. What's the limit as you approach -1 from below, going that? There isn't one, right? It doesn't exist. And that's does not exist, right? So we'll just write that as DNE. So what's the limit as x approaches -1? Doesn't exist, right? Because it only exists from one side. And in order for this limit to exist, the left and the right-hand limit have to be the same, right? They both got to be coming to the same place. What's the limit as x approaches infinity of f of x? 2, right? So as the x's get really, really big, then we're approaching 2. And what's the limit as x approaches negative infinity? Doesn't exist, right? Because the curve actually stops at. So one thing to watch out for here, especially if you have really old eyes, that are, is just sort of making sure that you can resolve that the printing's clear enough, and that you're, looking to say, is it -1 from below or that, right? Because sometimes you can get really confused if you're looking at it, you sort of misread the numbers. Actually, that's just me speaking. Sometimes I got really confused looking. I don't get it. X squared minus 3x plus 2 over 2 minus x. Did I graph that? Yeah, I did. So that's this one. Looks nice, but we know that that's not the true story, so what's happening where? Wait a sec. So at 2, it's undefined, right? Otherwise, it's just this nice straight line. So really, we need to put a hole in there, right? Or a point discontinuity. So the point discontinuity is 2, -1, right? So at 2, -1, there is a point of discontinuity, which you can't see, right? I mean, you can't, because it's a point, and points have no dimension. So equations of asymptotes. Are there any asymptotes here? No. The limit as x approaches 2 from above. -1. The limit as x approaches 2 from below. -1. The limit as x approaches 2. Okay. -1's all around, right? Make sense? Limit as x approaches infinity, so as x gets really, really large, where is f of x going? Negative infinity. And the limit as x approaches negative infinity, positive infinity. Okay. Yeah, good. Question? No? I went too far. X cubed minus 1 over x squared. Here's the graph of x cubed minus 1 over x squared. Is there a point of discontinuity? Is there an asymptote? Okay. So the point of discontinuity? No, none. And the equation of the asymptote, or asymptotes? Let's start with the obvious one. X equals 0. And then let's, what's this doing? Y equals x. Yeah, it's really right. Just lying along. That's called a slant asymptote, right? Because it's on an angle. And limits. So the limit as x approaches 0 from above, or in other words, as we go this way, from right to left, right? From above means coming at it from a positive direction towards a negative direction, right? So what's this limit? Negative infinity. What's the limit as we approach 0 from below? Negative infinity. So technically you could say it does not exist, right? But at this point, let's just be more specific. We'll say this is negative infinity. And this one is negative infinity. So what's the limit as x approaches 0? Negative infinity, right? Because it's the same from both sides. Right, and technically you could write does not exist, does not exist, does not exist. Your book answers will do that. They'll just say does not exist, does not exist. All right? we'll live with it. Just so that, you know, if you're looking in the book and it's saying does not exist, and you're saying, well, it should be positive infinity, you're probably right, and it's just we deal with it. Limit as x approaches infinity. Infinity. Limit as x approaches negative infinity. Negative infinity. Okay, leave that there. All right, and the next one. Two minus x over x squared minus 3x plus 2. Do we have any point discontinuities? X equals 2. How'd you figure that out? Right, okay. So, what's this factor? So there's a point discontinuity of 2, right? So they have opposite signs, right? So I got to throw that negative in. So there's a point discontinuity here at 2. Right, so what is that? 2, negative 1. And there's an asymptote at here, which is x equals 1. And we got some limits to figure out. Oh, sorry, are there any other asymptotes? Another asymptote, which is y equals 0, right? The limit as x approaches 2 from above. Negative 1, approaching 2 from below. Same thing there. And then the limit as x approaches 2 then is? Okay, so if the left-sided limit and the right-sided limits are the same, then the limit does exist and it is that value, right? So it's just negative 1. The limit as f of x approaches 1 from above. So we're coming this way. So what's that? Besides does not exist, it's negative infinity, right? The limit as x approaches 1 from below, or from the left, positive infinity. So what's the limit as x approaches 1? Does not exist. This is when it really does not exist, right? Technically, your book would just say does not exist, does not exist, does not, which in that case really is sort of true. Okay, but we're going to start to say, hey, this limit is negative infinity. If it's good enough for university kids, it's good enough for us. And this limit is positive infinity. And besides, he wrote the same book, so I don't know why he figured what. Yeah, but it was written in the late 80s. Perhaps they weren't capable. Didn't have all this technology either, right? I don't even know what graphing calculator would have existed at that time. When that book first came out. It wouldn't have been much. What's the limit as x approaches infinity? Zero. And x approaches negative infinity? Okay, so they're both 0, right? That's right. Our horizontal asymptote is what happens when we go way out, right? Either to the left or to the right, to infinity or negative infinity. Algebraically determining limits given the equation of a function. Okay, so we got 3 cases. Case 1, the function is continuous at a particular value of x. So the first one we looked at, f of x, x squared minus 2x plus 3 was a continuous curve. In this example, f of 2 exists. The limit as x approaches 2 of f of x exists, and the limit of as x approaches 2 of f of x is f of 2, right? Which means, or it can be shown, that if f of x is continuous when x is equal to a, then the limit as we approach a of f of x is f of a. Right? In other words, if you can just substitute the number in and work out a value, it's continuous at that point, and that is the limit. So example, determine the limit as x approaches 5. So what are we going to do? Well, we're just going to go and throw in a 5 and see what happens, right? Okay, let's put in a value of 5, and then let's see what happens. So that's equal to 5 squared minus 2 times 5 minus 3. Like, I don't see any initial problems, right? It's no problem because I'm not going to get a 0 down here. Which is what? 12 over 15? Which is what? 4 over 5? Okay, so the limit as x approaches 5 of that is 4/5, which is at that point, 5, that function is continuous, right? We don't have a point discontinuity, right? We'd be running into problems then. We'd have a 0 somewhere and say, oops. Like case number 2. The function is not continuous at a particular value. So in other words, when you try and work out f of a, you end up with 0 over 0, which isn't all that helpful, right? So for g of x, when determining g of 2, we got the expression 0 over 0. Although g of 2 does not exist, the limit as x approaches 2 of g of x does exist. How do we algebraically determine the limit? Sometimes factoring or rationalizing the expression will be helpful as shown below. Okay, so we're going to factor this, which is I think what we did anyways, right? So what was this? X minus 2. I mean, here's a hint. Usually this is one of the factors. So, I mean, if you're looking for factors, that's usually one of them. Okay, and then you can... So we've got the limit as x approaches 2 of x minus 1. So now we put in the value of x, which is 2. So we go 2 minus 1, which is 1. Okay. So we can simplify that expression, really. And we say, I mean, we know this from before. Right? We know that this graph is the exact same as this graph, as long as x isn't 2, right? If x is 2, then they're not the same. And that's. But we're not interested, right? We don't want x to be 2. We want x to get as close to 2 as we want it to get, but not be 2. Except up here. Here it can be 5. That's fine, right? Because it's continuous. Okay. Questions? And we're going to do a bunch of examples, like now. Okay. Determine the limit as x approaches -3. So we can see we're going to have a problem, right? If x is -3, then we're going to end up with a 0 in the denominator. And what would we get up here? We get like 9, 18 minus 20. This would actually work out to 0 over 0, right? So this would be 0 over 0. So we need to use some strategy, and that strategy is, let's factor. So this is equal to the limit as x approaches -3. So this stays there, right? That limit. It's an operation, right? It doesn't go away until you can actually do it. And right now we're not able to do it. So on the bottom we got x plus 3, which means on the top we must have an x plus 3. So this has got to be 2x plus 1. So I'm not really factoring, I'm sort of faking factoring. I'm just saying, well, you know, if x plus 3, then this one is 2x, and it's okay. 2x squared plus 6 plus 7. So anytime you factor, always check, right? Because if you get your factorization wrong, then everything goes bad from that point. Okay, so we've got this, which means this is equal to the limit as x approaches 3 of 2x plus 1. So we're now canceling the x plus 3's, which is, and now we can drop the limit because we're going to substitute. Oh, sorry, it's -3. So 2 times -3 plus 1, which is -5. Okay, and important, if you have questions, make sure you ask. Okay, next one. -2. -2 squared is 4. 4 minus 4 is 0. Negative 2 cubed is negative 8, plus 8 is 0. This is going to be a 0 over 0, so we've got to do something. So we're going to factor. So that's equal to the limit as x approaches. So we still leave that, right? We're not getting rid of that limit until we can actually go and substitute in and get ourselves a valid expression. So x squared plus 4 is x plus 2, x minus 2. X cubed plus 8, that's a sum of cubes. That's factorable. And if I remember the acronym SOAP, so that means that, so you're taking cube root. So the cube root of x cubed is x, the cube root of 8 is 2. So same sign, so it's x plus 2. And then we get an x squared, then we get the opposite sign. Okay, and then that's like, wait a sec, that's 2x or 4x? I think that's 2x. And that's 2x minus 2x. And then always positive, so then plus 4. Now I better check that, right? So I got x cubed minus 2x squared plus 2x squared plus 4x minus 4x plus, okay, so that's good. Okay, so I gotta check those because especially with sum or difference of cubes, right? I don't do that often enough to, I mean, you know, this I know is this, I'm not checking that, that's good. Okay, so these guys go in. So it's the limit as x approaches negative 2 of x squared minus 2x plus 4 over x minus 2. So things are okay now, right? Because that's, you know, negative 2 minus 2. It's not going to be 0, so we're good. Now we can substitute in. So we have negative 2 quantity squared minus 2 times negative 2 plus 4 over negative 2 minus 2, which is, what do we got? 4 plus 4 plus 4, so that's like 12 over negative 4. Which is negative 3. So if I wanted to sort of, you know, I might graph that just to kind of look at it and just say, does the graph match up with this, right? Like if I had, if only there was some way to graph this, which I don't think I actually put that one in. Yeah, it's not one of the ones I chose, but you know, we could. Do you want to graph it, or? I mean, I'll graph it. What was it? Y equals. Yeah. Sure. Y equals x cubed. Move that down. Plus 8 over x squared minus 4. And what were we looking for? What were we looking for? Negative 2 or something? What was it? Yeah, right. So you can see at negative 2 it's undefined, but as we approach from above, our values are getting close to negative 3. And if we approach from below, then our values are going down, getting close to negative 3, right? And we actually have a hole. Or a point discontinuity. Wow, okay, not going to be much room to do this. Let's see if I can do fancy. All right, apparently not. Oh, wait, I don't even have a pen anymore. Okay, what we're going to do here is we are going to rationalize the numerator, right? I mean, the problem is as x approaches 2, x minus 2, we get a 0. So what our thing here then is we're going to rationalize the numerator. So make this like, let's see if I can make this like really big and then. that'll give me room to write. There we go. Okay, so the limit as x approaches 2, so we've got the root of x plus 7 minus 3 over x minus 2. We're going to multiply that by what? Root x plus 7 plus 3 over root x plus 7 plus 3. Now, there's an equal sign here. Okay, so it equals the limit as x approaches 2. All right, so we know what we're going to get out of this, right? We know when we do this, so we've got this times this, which will just be x plus 7. We don't need to worry about the inner and the outer. We're going to FOIL it, but the middle terms are gone, and so we've got this squared minus this squared. So it's x plus 7 minus 9 over x minus 2 and the root of x plus 7 plus 3. What's x plus 7 minus 9? X minus 2. So this is going to cancel with this, right? Leaving a 1. So it's the limit as x approaches 2 of 1 over the root of x plus 7 plus 3. Okay, so take a look at that, make sure you're good with that, right? Say, oh, hey, look, that by rationalizing the numerator, we actually got an expression which was equivalent to the problem denominator, right? The problem denominator being x minus 2 if you're substituting a 2 in. So now that's gone. These guys are gone, leaving me with a 1 up here. It just doesn't disappear. You don't put a blank above the line. Okay. Now, can we stick a 2 in there? Sure, right? I mean, that's fine. So that's equal to 1 over the square root of 2 plus 7 plus 3, which is 1 over 6, right? So 2 plus 7 is 9, the square root of 9 is 3, 3 plus 3 is 6. So we get 1 over 6. Fancy, huh? Let's go back to that. Look, it all fit in that. Okay. Questions? Concerns? No? Looks like we'll actually have some time at the end, I hope. We don't have too much more to do we? No, definitely not. We will definitely have some time at the end so you can get started on, or ask me any questions about the first couple of days worksheet. So if you have any questions on those, I'd be happy to go through any of that with you. You can start working on limits. Tomorrow's work period just on limits. So page 18. Just remember, they're going to say does not exist. We're going to say, yeah, really? Come on. Okay, the limit as h approaches 0 of 4 plus h quantity cubed minus 64 over h. Problem. We put 0 in there, we're going to end up with 0 over 0, right? This is one of these guys that's a 0 over 0. So we're going to factor it. This is a difference of cubes, right? That's one of the things being cubed, and that's the other one. So how does that factor? So it's the limit as h approaches 0. So it's the, what is it? One of the factors has the same sign, so it's going to be 4 plus h minus 4. So that's your first factor, right? It's like a minus b. Just think of 4 plus h as being a. And right now we're looking at a cubed minus b cubed. So that's a, that's b. And then it's a squared, so it's 4 plus h squared. And then the opposite sign, so we got a plus. And then it's ab, so that'll be 4 times 4 plus h. And then it's b squared plus b squared, so that'll be 16 over h. Okay, so I'm going to check that, okay? So I've got 4 plus h cubed plus 4 times 4 plus h squared minus 4 times 4 plus h squared plus 16 minus 16 minus 64. So it's all good. It's all good, right? Oh, little equal sign in front here because that's equal to. What's 4 plus h minus 4? H. All right, so here, let's equals the limit. Okay, so we have h times forward time. Okay, so h is gone now. We can substitute h as 0 into the expression now, right? It's allowed because we won't end up with the 0 in the denominator. So we get 4 plus 0 squared plus 4 times 4 plus 0 plus 16, which is 16 plus 16 plus 16, or 48. Good. This will all be up. So I'm going to save these as a PDF and I'll stick it up in Schoology as well as the whole thing. Assuming it's still recording. I don't know. Yeah, I see numbers still counting. Determine the limit as h approaches 0 of 1 over 2h minus 1 plus 1 over h. So we got a problem. We get like 1 over negative 1, which would be negative 1 plus 1. So this would work out to 0 over 0. All right, so we have to do what we can. So it's the limit as h approaches 0. So what we're going to do is we have a common denominator of 2h minus 1. That 1 up there is good. Plus, so all I'm working with right now, forget the h on the bottom, right? Actually, let's put it out here. There's the h from the bottom. It's right here, right? Times 1 over h. Dividing by h is like multiplying by 1 over h. So we're just doing this. So common denominator is 2h minus 1, which means this needs to be a 2h minus 1. So what's 1 plus 2h minus 1? It's just 2h, right? So this is the limit as h approaches 0 of 2h over h times 2h minus 1. Okay, so we've canceled the h's. So now we've eliminated the problem, right? Which is if I stick a 0 in here, put a 0 in here, I have a problem. So we're dividing by 0, but now we don't have that problem. So that's 2 over 2 times 0 minus 1. So in the end, this is where the limit drops off, right? When we no longer write limit, because now we're actually going to just substitute in the value. So that's 2. So negative 2? What did I mess up? Oh, 0, yeah, 0 minus 1 is negative 1. Negative 2. Nice. Easily changed, no erasing. Good catch. It's your job, right? Besides learning this, it's like catching errors. Otherwise, we'll spend 4 pages. Okay, so you have some strategies now to apply, right? Can I factor and cancel? Can I rationalize the numerator? Last case, if f of a equals k over 0, so for h of x equals 3 over x minus 2 squared, when determining h over 2, we got the expression 3 over 0. In this case, the limit does not exist. True and not true, right? I mean, for sure, the limit does not exist, but the question is, does it do this? In which case, we will say what? The limit is infinity, or does it do this? In which case we say, hey, that limit really doesn't exist because you have one branch going. So we'll live with does not exist. So if you work something out and you say, hey, if I throw a 2 in there and I get 3 over 0, I'm just going to say the limit doesn't exist. I'm not going to bother to look at it to see which one it is. Okay. Now in this case, it's sort of, in a sense, obvious because this squared means this is always going to be positive, right? So as you're getting these values close to 2, whether you put 2.001 in there or 1.999, because you square them, although one was positive, one was, they're both going to come out to the same number, right? So it's going to be, and it'll be positive, so this thing is going to go to positive infinity as a limit. Okay, so determine the limit as x approaches -1 of x minus 1 over x squared minus 1. So again, we just try our little thing here. Okay, so you say, hey, look, I ended up with -2 over 0, so this is really this limit. So the limit as x approaches 1. So we say the limit as approaches -1 of x minus 1 over x squared minus 1 is, does not exist. So I can say equals does not exist. So it just does not exist. Okay. And you could always throw in your graphing calculator and just look at it and say, because actually it'd be obvious in a graphing calculator, right? Do they both go up? But does not exist, perfectly fine answer, gets you all the marks that you need. And I think, what else? We just want to look at some stuff. So in summary, when determining the limit of f of x, if it's continuous, then the function exists at that value, and the limit as x approaches a of f of x is just f of a. So we're always just going to try and substitute in and just say, hey, do I get a value? Yeah, I do. Okay, then that's it. If it is not continuous and you end up with 0 over 0, then we change the expression by factoring, rationalizing denominator, rationalizing numerator, or simplifying, and then substitute x equals a. If it is, if f is not at continuous, not at, that doesn't. If f of x is not continuous at, the x. Wait. There, that would make more sense. Maybe yours even says that.
For the one before, couldn't you have done difference in squares to solve it, or is it unsolvable? For the one above.
Let's go back. We'll go back and look at it in a second. I'm just sort of curious about it too, because yeah, we could have done it in squares and canceled and ended up with 1 over x minus 1 or whatever. But the problem is, what would have canceled? Would we have ended up with x plus 1 on the bottom?
Yeah.
So then when we substitute -1 in, we'd still end up with 1 over 0. So it would still be does not exist. Like we still wouldn't get a value, but our question really is it does not exist, or is it a positive infinity? We can actually kind of figure it out by let's take that, but we'll do that in a second. So if you get k over a, then the limit does not exist. We have some properties of limits. These are also in the textbook, I believe. So if the limits both exist and c is a constant, then the limit of the sum of two functions is equal to the sum of the limits. And differences, same thing. And what? They're leaving 3 for us to fill in for ourselves. If you have a constant times a function, then you can just take, so if you have the limit of a constant times a function, you can just pull the constant out front and just take the constant times the limit. Okay, so that works. The limit of a product of two functions is equal to the product of the limits. The limit of the quotient of two functions is equal to the quotient of the limits. The limit of a function which is raised to a power is equal to the limit of the function raised to the power. Okay, so if you have that situation, you can just say, I'm just going to find the limit of f of x, and then I will raise it to the power. Okay, so, and then if we have a radical, then it's the same thing. We can do the nth root of the limit. So those are the properties of the limits, and they are also listed in the textbook, so you'll have them there to look at. Ooh, done early. Wow, you have lots of time. So what was one we were going to look at? Yeah, so all right, so if we took this and just sort of said, so limit So problem number one, okay, it's still going to be 1 over 0. But question is this you know, thing or so how do we do? So if we say, okay, limit as x approaches -1. So you want to look from above and from below, right? You have to do both sides. So as x approaches -1 from above, so like what's above? Let's say 0.9, -0.9, then this will be negative. So we'll have -0.9 minus 1. And x squared, that'll be positive but less than 1, so this will be negative, so it'll be like positive infinity, okay, as we approach from above. If we approach from below negative, this will be negative again. This will be larger than this, so you'll have a negative over positive. So one branch will be positive as we approach from above, it'll be positive, from below it'll be negative, so it really doesn't exist. Okay.